Hi, welcome to Background 1 Electric Field Plotting. We're going to start with electric field vectors and electric field lines. Electric field vectors point O. So the equation for the strength of electric field is given right here, and the K constant is right here. This is for a charge of Q, and this is the electric field at a distance R from that charge. So I recommend you look at this website and play with it. I'll show a little bit right here. The electric field of a positive charge points away from the positive charge, is stronger when we're closer to the positive charge, and weaker when we're away from the negative charge. That's shown right here with this r squared. When your r is larger, the electric field is weaker. So this can measure that. Then the electric field of a negative charge points inward towards the negative charge. Electric field points inward towards the negative charge. If you have two negative charges, the electric field directly between them, it goes to zero. Because this one will have an electric field to the right, the other one has electric field to the left, and they cancel at the middle. Same with positive charges, or one positive, one negative, you get an electric field towards the negative. But if you have two positives, then the electric field directly between them becomes zero. Electric field away from positive charges towards negative charges. The force of a charge in the force felt by a charge in an electric field is given by this equation. So if we have an electric field that points to the right, and we have a proton in this electric field, so this is our electric field. I'll do one more. If we have a proton in this electric field, then it will feel a force in the same direction as the electric field. If we have an electron in the electric field, it will feel a force opposite the direction of the electric field. And then the magnitude of force is given just straight by this equation. The electric potential, I think, is the most important part of this unit. So electric potential, it's kind of hard to understand, so I'll start with an analogy to temperature. So temperature, every point in space has a temperature. You can put a thermometer anywhere and just measure that temperature. Electric potential is the same way. You can take any point in space and just measure the electric potential at that point in space. Sometimes the electric potential for, let's say, the electric potential or the temperature electric potential was the same on my entire Apple Pencil, then it would be an equipotential surface, equipotential line, right? If this was just a line, then it would be equipotential line. If the temperature is the exact same on this entire candy pack, then we'll call this an equipotential surface. Because it's a surface, it's not a line. This is a line, not a surface. Equipotential. If you've ever learned isotherms, those are just lines of equal temperature. It's the same thing, just equal electric potential instead of temperature. Electric potential matters because electric fields point from high electric potential to low electric potential. So, in a room temperature with different temperatures, the gas flows from a high temperature to a lower temperature because the pressure is higher where the temperature is higher. The electric field in space points from higher electric potential to lower electric potential. So in this diagram, we would have a high electric potential on the left and a low electric potential on the right. because electric fields point from high electric potential to low electric potential. Um, if so, then if I said, or so we're given this equation, this E, the relating electric fields and electric potential. So if the electric field was of strength 5 newtons per coulomb, or coulomb is the unit of charge. That was the strength of the electric field, and this is a 2 meter distance, then the electric potential would drop 10. So we could say maybe this could be at like 5 volts, and this could be at negative 5 volts, and that would be a drop of 10. So by plugging it into this equation, we can see if this is true. So we have electric field of 5 is equal to change in electric potential, negative 10, and then we have a negative in front, and our distance was 2. So that is correct. We did that right. So that's how that equation works. The negative sign is just the direction of the electric field. So if we said the distance, we did our distance from left to right. That's how we took our distance. And so without that negative sign, then we would get a negative 5, meaning like negative 5 to the right because that's the direction of our distance. But a negative 5 to the right is the same as a 5 to the left, which is the wrong direction. Our electric field is 5 to the right. So we need that negative sign there to make sure that the math works out and our vector points in the right direction. So we find our electric field to be 5 to the right. So that's kind of a lot, pretty fast, but you'll get more review in the actual class itself. So this gives us some rules. Electric field lines do not intersect. Let me turn off. Electric field lines do not intersect. Why? Because if we look back at our thing, electric field vectors always point in a direction, right? So let's say they're pointing in this direction, and then the electric field line points in the same direction as the electric field vector. Always, always, always. They're always in the same direction. That's what the electric field line comes from. If we had two electric field lines that intersected, that means at this point of intersection, the electric field vector points in two directions, which is not possible. Your electric field vector always points in one direction. It can't have two directions. That's like saying, like, I have 5 fingers and 6 fingers at the same time. Like, you can only have 5 or 6. You don't have 5 and 6. So your electric field vector points in one direction, so your electric field lines cannot cross. The magnitude of electric field is larger when electric field lines are together or closer together. So if we have a proton and then electric field lines radiating out, we know the electric field is stronger when it's closer to the proton. If we measure this distance between these two electric field lines, it is much smaller than the distance between those two. So when the lines are closer together, we know that the electric field is stronger. When the lines are further apart, the electric field is weaker. Electric field lines begin on positive charges and on negative charges. I said that already. They extend out to infinity if no negative charges are present. They cannot end in midair. In electrostatics, the magnitude of the electric field is 0 throughout conductors. So let's draw a conductor. If we have an electric field within the conductor, right? Because charges are free to move within conductors, if we have an electron over here, he will then feel a force to the left. So when he feels that force, he will accelerate and move to the left. So our electron now ends up over here. The force goes to zero and the electric field goes to zero because the electron has his own electric field pointing towards him, canceling out the original one. So the electric field goes to zero. If you ever have an electric field inside of a conductor, the charges will just move to set that electric field to zero. In electrostatics, there are never moving charges. Electrostatics is the study of stationary charges. So if all charges are stationary, there cannot be any electric field within the conductor. So conductors have no electric field. I hope that makes sense. Because of this, conductors are electric potential surfaces. So going back to our equation from before, we have, rearranging it, we have change in voltage is negative, change in E times, E times change in D. That's the equation rearranged. So if the electric field is zero in some space, then that means the voltage is equal to zero. The change in electric potential difference is zero. So that means the entire space of the conductor must be at the same electric potential. So it's an electric potential surface, equipotential surface. Because it's equal potential, equipotential, equal potential. So conductors are equipotential surfaces. Then electric fields are always perpendicular to equipotential lines and surfaces. So let's say we have an equipotential line here. Make that. Let's say we have an equipotential line of 3 volts right there, and another equipotential line of 1 volt. No, just the 3 volt for now. And then we have an electric field parallel to that. The voltage drops along the electric field line. We've covered that already. That's just this equation. So because the voltage drops across this line, then the voltage at this point, start, is higher than the voltage at end. If these do not have the same voltage, then this is not an equipotential line. Definition of equipotential line is the same voltage across the whole thing. It's like the definition. So because of that, we cannot have any electric field vectors parallel or any components parallel to the electric potential equipotential lines. This means that electric field vectors are always perpendicular to equipotential lines. So, and they point from high to low equipotential. So that was the 3 volt, and this is the 1 volt, and they'll point towards the 1 volt. Right? Because they point from high to low equipotential. Electric field lines are always perpendicular to conducting surfaces. So because this conductor is an equipotential surface, then the electric field lines must be perpendicular. It's an equipotential surface because it's a conductor, and the electric field is zero within because any electric field within will move the charges to remove the electric field. So electric field is always perpendicular to conductors. Equipotential lines and surfaces do not intersect. This should make lots of sense. If our 1 volt equipotential line intersects our 3 volt equipotential line, then at this point of intersection, it is 3 volts and 1 volt at the same time. This is impossible. It's the same thing. You cannot have 5 fingers and 6 fingers. You can only have 5 or 6 on the same hand. You won't have 5 and 6 fingers at the same time, unless you're talking about while your finger is getting chopped off. That's that. So just to put all these things together into a diagram that's hopefully easier to understand than my rambling, let's say this is our graph of electric potential. So maybe my iPad has higher electric potential over here and then a low equipotential down here, and is low, and then you have like two electric potential peaks up here. So like it's just a surface, but it has electric potential, and that graph is a graph of the electric potential. Um, the the graph is higher at points of higher electric potential, lower at points of lower electric potential. So this is like the electric potential of a 2D flat surface. Okay? If we wanted to draw equipotential lines on our electric potential, it would look like this. So the electric potential lines so here we can see if we were to draw a circular, like a circle of the same height on this graph, we would end up with that yellow circle. So all these are lines along the same height of voltage. So we can see here with this graph legend, that here this yellow line is 6 volts along the entire line. It is 4 volts along this entire line, or whatever. Maybe this is like 5, and then this is like 4, and then this green one is like maybe like 3, and then 2, and this is also 3. So we can tell that it's higher over here and lower over here, and so our but these are equipotential lines of our electric potential. Equipotential lines are drawn here. If we wanted to draw the electric field, we know that it points from high electric potential to low electric potential. So it would point from this yellow down the slope, and then it would point from this tip top down the slope. The electric field lines would point from this peak down the slope, and this peak down the slope, this peak down the slope, and they would end down here at this pit. So we can see that here. It points from the top to the bottom of our slope, top to the bottom of our slope. And then here we're pointing from the top to the bottom of our slope, and they don't point out of the bottom, they stay at the bottom, they point out of the top into the bottom lower electric potential, point from high to low electric potential. Electric field lines are similar to the electric field vectors. They're always parallel to the electric field vectors, and they just kind of follow them. But they start at peaks and end in pits. And they don't end or start anywhere else. They just go out to infinity everywhere else. You can see the field vectors are much shorter where the field is weaker, and the lines are further apart where it's weaker. So the lines are shorter, and the electric field vectors are shorter, and the equipotential lines are farther apart where it's weaker. And these are also farther apart where it's weaker, and very close where the electric equipotential lines are close together. Here the equipotential lines are very close together, and these lines are very close together, and these lines get much longer. So putting it all together, you can see this down here is all of them together. So where the equipotential lines are close together, the electric field vectors get longer, and the electric field lines get closer together. Yeah. So this is what our lab today is all about. Okay. Hope that was helpful. Let me know if you have questions.